So, ladies and gentlemen, I think we can get started. My name is Armagan Al-Haq. I'm the manager with the Waterloo Institute for Sustainable Energy here at University of Waterloo. And it's an honor and privilege for me to introduce our guest speaker for today, Professor John Simpson-Porco. Professor Simpson-Porco is an assistant professor in the Edward Samuel Rogers Senior Department of Electrical and Computer Engineering at the University of Toronto. His research focuses on feedback control theory and applications of control and optimization in power and energy systems. Professor Simpson-Porco received his bachelor's degree in engineering physics from Queen's University in 2010 and his PhD in mechanical engineering from the University of California, Santa Barbara in 2015. He was previously an assistant professor of electrical and computer engineering at the University of Waterloo, Canada, and a visiting scientist with the Automatic Control Lab at ETH Zurich, Switzerland. He is a recipient of the Automatica Paper Prize, the Center for Control, Dynamical Systems and Computation Best Thesis Award, and the IEEE PES Technical Committee Working Group Recognition Award for Outstanding Technical Report. He is currently an associate editor for IEEE Transactions on Smart Grid. So I would like to welcome Professor John Simpson-Porco. Professor Simpson-Porco, the stage is all yours. Please go ahead.
Thank you, Armagan, and thank you for the invitation to give this seminar. I know we've been playing email ping pong maybe for a year or two, trying to organize something, so I'm glad we can finally do it. So my plan today is to go for about 45 minutes, and then maybe there'll be some time for questions. And the talk is a bit of a hybrid talk, so there will be discussion of modern problems that are arising in the power system. And my research focuses on feedback control, so I'm going to be mostly talking about how you can try to meet those problems using ideas from systems and control theory. Okay, so to frame our discussion, so here's a sort of diagram of a classical power transmission distribution system. And what this is you have a transmission network, which is at high voltage that feeds power sort of unidirectionally to a medium voltage distribution system, then to a low voltage distribution system, and then finally to consumers that are, for the most part, attached to the low voltage distribution system. And what feeds into the system is power from large bulk generators, typically synchronous generators powered by fossil fuels. So that's the classical generation paradigm. And what we're seeing in the current system is that bulk centralized generation is being replaced by generally smaller scale and more distributed generation sources. So think about the shutdown of coal plants in Ontario over the last decade or so, and the rise of, for example, wind generation in southwestern Ontario. And the big difference there, or one of the big differences, is that you're no longer using synchronous generators to interface that power into the system. You're mostly using power electronics. And the kind of inherent properties of those devices are quite different, and that makes for interesting control problems. One of the problems with renewable-centric systems is that you get an increase in uncertainty, and you have to try to account for that using forecasting and using feedback control. Another interesting property is when you move from a system that has bulk centralized generation to a system with more small scale distributed generation, the kind of information patterns in the system become more distributed and less centralized. So you're not just going to be taking actions at the bulk generation level over here. You instead have 1,000 little generators dispersed throughout the medium and low voltage system that you need to coordinate. Luckily, we have tools to do that coordination now. So we have high bandwidth sensors and actuators that we're deploying in the system, such as phasor measurement units, that allow us to try to meet some of those challenges. So there's challenges associated with this transition, but there's also new opportunities to take advantage of these devices. So here's a sort of sketch of some of the research that goes on in my group in the area of control and optimization of energy systems. This is all a bit tangential to what I'll try to focus on today, but I thought I'd mention it. So I have an ongoing set of work on control and optimization of microgrids here. This is in collaboration with people at the University of Chile, and some work on active distribution systems where you're trying to coordinate flexible devices within the distribution system to optimize operation. And then some ongoing projects on frequency control, one with the Electric Power Research Institute, and some more recent work on re-examining classical automatic generation control and trying to think about upgrades to that system that would be appropriate in the modern setting. So that's just to mention some other things going on in my research. So I'm a control engineer. I come at all these problems in power system modernization from a control engineer point of view. And what we do in control is we make things reliably boring. That's the goal of control engineering, is we want things to operate in a predictable, boring fashion. And that this should happen despite uncertainty, which affects the system, and disturbances. So here's sort of my sketch of interesting control problems that are happening in the current system. So you're going to need to control and coordinate many different kinds of resources. And you would like to do this in a real-time fashion and in some optimal fashion. And you would like performance guarantees for the methods you develop. So if you can coordinate lots and lots of different resources in a very efficient fashion, then you're meeting the challenges associated with this transition to a more distributed generation architecture. Associated with that is how you have to think about the architecture of information within the grid. So that's sort of the flow of information from sensors to actuators to algorithms and IT infrastructure in the system. And you end up getting forced towards more hierarchical structures. So that's something that that's sort of a theme that's going to recur throughout the talk, is hierarchical layering of information and control. And then you can't just apply sort of any crazy control ideas that you want to cook up to these systems. You do have to try to integrate with the conventional approaches if you want to have something that's actually going to fit into the system one day. So you really need to be thinking about integration with legacy systems when you're designing these control strategies that you want to address these problems. And you want these solutions you develop to be simple and congruent with what people in the power engineering sector already expect and understand. So sometimes in a lot of control work, this third constraint here gets dropped, but it's quite an important constraint. So let me give you a few examples to motivate the kind of problems that are driving my research right now. So here's an example of a distribution feeder. And in this distribution feeder, you have different kinds of resources. So here's a solar farm, some batteries, some wind turbines, some houses, and so on. And what generally happens is that voltage levels in this feeder will fluctuate quite a bit as the amount of renewable energy that's pumped into the system varies over time. So this would be sort of a typical plot. This is data from a feeder in California. And what's happening here is as the sun rises, these solar panels are injecting power into the system, and that pushes up voltage levels. And what you would like from an operational point of view is for those voltages to be controlled below some limits here. And this kind of violation, you generally don't want that. So if you start to try to formalize this problem, you could try to write down a model where you compute the voltages as some function pi of the solar power inputs into the system, or some controllable inputs rather, and the uncontrollable inputs, which in this case might be the solar power. And you could try to write down some sort of optimization problem that's going to flatten this curve up here for you, and make use of the controllable sources you have within the system, maybe these batteries, in order to flatten out that curve. And what you'd want is a online control system that's going to do this for you. And you want that control system to be very robust to the model you have of this grid here, because that model is going to have a significant amount of uncertainty. So that's the first kind of question that I would pose, is how could you think about designing these kinds of control strategies? Second example, again, thinking about voltage, but this time in the transmission system. So this would be a simple diagram of a single line transmission system. And you have different kinds of controllable resources in the system for managing the voltage. So you have synchronous generators here and devices called static VAR compensators, which can be used to manage voltage levels. And you also have inverter-based resources that are maybe interfacing batteries or batteries and wind farms and solar farms and so forth into the system. And so you have different kinds of resources you can use to try to take control actions. What you would like to do is use those resources in a smart way such that the voltages in the system remain within operational limits. So here's an example where a voltage is dipping down below this operational limit, and we'd like to avoid that kind of behavior. So you can, again, try to write down some sort of model to describe the system. This time it's a differential equation model because this is a more dynamic kind of system here. And you would, again, ask the question, how do I design a controller that's going to make efficient use of these different kinds of resources I have within the system in order to make sure I don't get these voltage violations here? Okay, final example. This one is again in the bulk transmission system, but now we think about the control of frequency. So that's the frequency of the AC power signal. And this is a typical response of the system to a disturbance. So let's say a generator trips out of the system and fails. The frequency will decline. Control systems will act to arrest that decline, and you'll come to some nadir down here. And you'll generally come back up to some constant value. And then there's another control system, secondary control, which acts on a longer time scale to restore the frequency all the way up to its nominal value. So that's the goal of secondary control. It tries to bring that frequency back to zero despite disturbances in the system. So here's a block diagram of how this sort of looks then. So you have load or generation disturbances which are affecting the system. You have some controllable devices that you can send power set points to, and then you're going to get measurements of frequency out of the power system here. And you could think about the same kind of problem of designing a controller based on an optimization problem that's going to make optimal use of the resources that you have in the system. So you would like to design the best set points possible to achieve your goal of bringing the frequency back to zero. And you would write that as a minimization of some cost of selecting those set points. And you need to take into account here the dynamics of the system. So you can see there's this dynamic response that happens. You'd like to take that into account. And again, what we would want is, okay, based on this kind of formulation, how do we design a control loop that's going to do this in real time for us, that's going to optimize the resources we have within the system in order to achieve, in this case, frequency regulation. And a more subtle question is, what kind of architectures are permitted for that kind of control scheme? Where does information have to go? What measurements need to be taken? Where do they need to be sent? And so on. So these are sort of the broad questions that are motivating a lot of the research that I'll talk about today. So what this all sort of coalesces into in the framework that I deal with, which is control, is this kind of block diagram where you have a physical system, in this case the power system, that you're taking measurements from. And those measurements are going to be fed into some algorithm here, which is going to process those measurements and produce commands to send back to the system. And the goal is to use the measurements in a smart way to produce commands that deal with disturbances that affect the system and deal with uncertainty that you have in your model of the relationship between measurements and commands. So the approach I'll be presenting today is something called feedback-based optimization. And I'll try to insert into this block here that we need to design an optimization algorithm that's sort of inspired by traditional approaches in convex optimization. And we're going to use that to generate these commands, which are going to sort of optimally deal with these disturbances that are affecting the system. And I have two frameworks for this. I will probably focus mostly on the first framework in the interest of time. But this framework really begins from the starting point of thinking about optimization and trying to leverage some of the methods that have been developed there in optimization and bring them to control problems in the power system. So the key ingredients that we're going to be using here are some ideas from convex analysis and optimization, and some ideas from a field called robust control as well. Okay, so here's the setup that I'd like to discuss. And we're going to represent things using this kind of block diagram here. So we have some inputs into our power system that we want to design. There are disturbances W, which affect the power system, that we generally are not able to measure, but we would like to deal with in some sense. And then there are measurements that we can take from the system. And there's a relationship pi that is a function mapping the inputs and the disturbances into the measurements. So here's an example from before. So our disturbance here could be solar power generation that's entering our distribution feeder. We're going to be measuring voltage at different points within the feeder in order to get some idea of what's happening in the system. And what we can send our power set points, this is called real and reactive power, we can send those set points to, for example, the batteries within the system here in order to try to mitigate the effect of the solar on the voltage. And what we'll try to write down is an optimization problem that describes the engineering specification that we'd like to solve. So what we'll do is we're going to try to minimize a cost of selecting the inputs. So that's what I call f of u, and then a cost of the measurements that we take from the system. So you could think in our example here of this cost as representing voltage deviations outside of the limits. So this term would be telling the optimization, I want to keep my voltages within limits. And this term would be telling the optimization, well, I should try to make efficient use of the resources U within the system. And this minimization is subject to the fact that there's a relationship between U and Y. So we know that the measurements are produced by some function here of the inputs and the disturbances. So this is a constrained optimization problem. And we're thinking about this sort of as a steady state problem. So I'll come back to that in a minute, but just think of this as a static steady state problem. Oh, and I should say, so this minimization should also be done subject to limits on the control signals, because generally you have some limits there in terms of, for example, power set points. You can't have them be too big or too small. They have to be within some limits. So that's captured here. Okay, so here's the key idea of the methodology, and you can express it just in one slide. So here's our optimization problem. And the first thing I do is I'm just going to eliminate y, because I've got a formula for y here. I can plug it in to the optimization objective function up top, and I get this simplified optimization problem. And a very classic method for trying to solve this kind of optimization problem is called projected gradient descent. So you would begin from some initial guess of what's the best u that I should plug in here, and you would perform a sequence of iterations. And those iterations are obtained by trying to look at the the value of the function here and trying to make it smaller. And that's captured by checking the derivative of this function, which is this gradient here, and trying to move in the direction of the negative gradient. So that's called gradient descent. Then you put a projection outside in order to account for the constraints. That's called projected gradient descent. Okay, so this is the formula then that we've got if we wanted to use this projected gradient descent. And there's a number of issues with applying this formula. So first of all, one issue is that I said the model pi is, we want to be robust to uncertainty in that model pi. And a lot of the times, you might not have a great model, actually. So this function pi, we don't know very well. So I can't really plug it in there. If I don't know the function pi very well, then I probably don't know its derivative well here. This is the matrix of partial derivatives of this function pi with respect to u. Okay, so there's two pieces in this that I don't know very well. So you start trying to figure out how you might deal with this. So one way to deal with it is, well, how about I just take this piece here that I don't know very well and I replace it with an approximation. And I'll just call that capital pi. That's some constant matrix that I get to choose. And I hope I can insert a good approximation here so that this formula is not too different from this formula. But in any case, I would insert this approximation, and then I've at least dealt with one source of uncertainty there. I still don't have a great model of this function pi, but what I do have is, remember, I have measurements for my system. So pi of u, w, that was exactly the formula for the measurement that I'm going to be taking from the system. So I can actually just take a measurement from my system and plug it in there into that function gradient of g. So with those approximations, we get something we call approximate online projected gradient descent. And it's approximate because we've included this approximation here of the sensitivity matrix pi. And it's online because we're going to be using this real-time measurement from the system. And that's our formula for online approximated gradient descent. So back to our example. Let's say you take this idea, you apply it to this problem. I'll come back a little later to some of the specifics of how we implement that. But what you now have is you have an algorithm, which I call C here. It's a controller, and it's going to take this voltage and produce power set points to feed back into the system in order to mitigate the solar variations. And here's the kind of results that you can generate with this kind of control scheme. So this is the situation with the controller. And you can see that the voltages, they're now trapped below this limit. There's a little bit of violation there. You can get that to go away by further tuning the algorithm. But just contrast that with the situation down here without any control. So you're able to arrest the rise in the voltages due to the solar power entering the system. And what's less obvious is that behind the scenes here, the algorithm is trying to use all of the controllable resources in the most efficient fashion in order to achieve this outcome. Another thing that's not obvious but is hiding behind the scenes here in the analysis is that this methodology is very robust against variations in the model of the system that you think describes the real distribution feeder in this case. So you can be wildly wrong about the actual distribution feeder model here, and the algorithm will still produce results that are quite similar to this. And you can prove this. This methodology is very provably robust to quite large variations in the model. Okay, so that hopefully sort of piques your interest in, what are the nuts and bolts behind this methodology, and I'm going to tell you a little bit about that now. So this is the same formula as written before. So this is, for short form, I'll call this function here, which was the thing inside the brackets before, I'll call that capital F. And that's just a function of the control inputs U that we're going to select. And the update rule, the projected gradient descent, it can now just simply be written in this way. And you start asking the question, well, how do I try to analyze this kind of algorithm? What are going to be the properties of the iterations over time? And there's a theorem that you can pull out from a set of literature on what's called variational inequalities. And there are conditions under which this algorithm converges in a nice way. And those conditions are two conditions on this function f. So one of them is called strong monotonicity. So that's a property that this function, if you plotted it, it's sort of increasing. If you looked at any point on the function, yeah, it's increasing, and its increase is bounded by a minimum value rho. So think of that as a strictly increasing property, and then what's called Lipschitz continuity, which says the function can't increase too fast. So the function has to increase, but not too fast, is essentially the conditions that you put on this function. And then what you can show is that if you select the step size here, alpha, this is a tunable parameter, if it's less than the ratio of those two values, then this iteration converges. And you can say some other things as well, but it's not important for us. The problem that we need to address is that we're not really dealing with a standard with the standard setup that you would find in a textbook on optimization or variational inequalities here. So what we're actually dealing with is a situation where this function f is uncertain. And it's uncertain because we don't really know the model of the system here, pi. So we're uncertain about this function f, but we would like to still sort of leverage this idea and try to assert that the algorithm still converges and we get a nice stable behavior despite this uncertainty. So that's the problem we need to tackle is fine, these are the assumptions that are needed. How do I actually verify or systematically check those assumptions if the function f here is uncertain because we don't have a good model of the system? Okay, so this is where ideas from my home field of control start to come in a meaningful way. So in order to check those previous conditions, as I said, the conditions are that basically the function should be increasing, but not too fast. And you can start to develop a methodology for checking those conditions in a more systematic way. And the methodology that's used is to look at the matrix of partial derivatives, the Jacobian matrix of that function. And you can check those properties in terms of this Jacobian matrix. And it turns out that those properties are equivalent to this Jacobian matrix being positive definite. And of course, having a bounded Lipschitz constant as before. So you can express that in this sort of compact way here. If you fiddle with the formulas for long enough, you're gonna get to this formula here. Not clear why I'm rewriting it this way at this moment, but this is the form that we want to think about here. And in robust control, you deal with problems like this all the time. I want to verify that some inequality that's quadratic in my function here, delta f, I want to verify that this inequality holds despite uncertainty in this function f. And it turns out that this is a standard kind of problem that one encounters in robust control. So what you can do is start to leverage those methodologies from robust control and develop tractable computational tests for checking stability of these controllers. Okay, so the key idea is to actually overbound the uncertainty. So we know that our model of the system is uncertain. That's this function f. We need to have some sort of bound on that uncertainty so that we can try to capture it in a tractable fashion. Okay, so the idea here is we're going to overbound the uncertainty. Maybe I know that my model is in some smaller set here. I'm going to look at a bigger set, which I'll call J, and I'm going to assume basically that my model is always contained in that larger set of models J. And what we can do then is we can say, well, if the previous conditions that I needed are satisfied for all of the models in this bigger set J, then it's certainly satisfied for my original model because my original model was contained inside that set. And it turns out that now checking this kind of condition is tractable for very practical types of uncertainty sets J. And this is where the robust control stuff really starts to come in full force. I'm not going to talk about a lot of the details here, but you can use something called a linear fractional representation of uncertainty in this system. And this allows you to get to computational tests which are tractable. Okay, so some gory details here. I'm going to, for the most part, skip over these, and I'd just like to highlight what's the main result that you can get to at the end here. So you can actually check those conditions for convergence. So this strong monotonicity condition, that's that the function has to be increasing, and the Lipschitz continuity condition, the function cannot increase too fast. You can check those in terms of what's called a semi-definite program. And this is a kind of convex optimization problem that you can solve on a laptop computer. So for several hundreds up to maybe a few thousand variables, this can be solved, and you can get a certificate which says, yes, your uncertain model, even with all of this uncertainty that you have in, for example, the model of the feeder, it's still going to satisfy these conditions that you need for convergence of this controller. So let me come back now to the problem of voltage regulation in this feeder. And here's the details of how we formulate that problem. So we have a set of controllable resources in the system. This could be batteries, for instance, for simplicity here. And we can send set points for active and reactive power to those batteries. So what we're going to do is we're going to try to minimize how much we change those set points from the nominal values. Here I've written curtailment because I believe we originally formulated this for curtailment of solar energy. So let me frame it in that context instead. So these would be the set points to the inverters which are connecting the solar energy into the system. This would be the dispatch value of that solar energy. So for example, typically you would want to track the maximum amount of power in order to provide the maximum solar energy. And we're going to try to keep those set points close to that maximum power tracking value, subject to some limits. So I don't want to move my set points too far away, but I'm going to have to move them away a little bit if I want to deal with these voltage issues. And to deal with those voltage issues, you introduce this kind of penalty function here. And what this is it's a quadratic function that grows when the voltage violates your limits. But if the voltage is inside your limits, it doesn't do anything. So if you have no voltage problems, this term drops away completely. If you have voltage problems, then this term encourages you to change these set points in order to bring the voltage back within the bounds. And this is done subject to our model of the system, where the voltages are computed by solving the power flow equations given the set points PQ and the uncontrollable generation W, which enters the system. So to apply our methodology, this online projected gradient descent methodology, what you do is you replace the partial derivative of this model here, this power flow model, with a linearization. And that linearization I call pi nominal, and this can be computed in a quite standard way. Now, where does uncertainty come in? Well, this linearization is not perfect. So what we're going to do is we're going to say, well, if I looked at the real partial derivative of this power flow model here, that's what this is, I'm going to say that it's contained in a larger set, which is centered at my nominal linearization, but with an additive perturbation that is bounded in size. So I'm constructing a whole set of models. Right in the middle, I've got my nominal model, and this parameter delta here is capturing the radius of that uncertainty. And now you've got all the ingredients you need, it turns out, to implement those methods that I talked about in the previous slides. And you can actually provide certificates that if you implement that algorithm, it's stable under very large perturbations delta to the nominal model. So what we did was we sampled lots of different operating points from the system, and we basically took the nominal model as the average linearization and computed a value for delta, for this bound on delta. And we were able to show that using this methodology that even with very extreme operating points that you would never encounter in practice, that the methodology remains stable. So this is quite robust to variations in the system model. And so again, here are the results that you get. So this is a situation without any additional control actions. You get voltage violations here. And when you implement this online feedback optimization approach, you're able to keep the voltages within bounds, and behind the scenes, you're optimizing the use of all the resources within the system. And then finally, as I've sort of emphasized, you get these hard guarantees that for even very extreme perturbations in the system model, the closed loop is going to remain stable, and you're going to continue to get this kind of desired control behavior out of the system. Okay, here's another example, and this is something that we're working on in collaboration with EPRI. So this is the transmission system example, sort of applying the same methodology. And here, again, we want to select set points to these different controllable resources within the system. So we add generators, inverters, and static VAR compensators in order to keep all of the voltages within the system within their operational bounds. So that's captured again by some sort of penalty term on the voltages. We actually use the same one I showed on the previous slide. And then you have additional variables you'd like to keep within bounds. So you want to keep the powers that these devices generate within bounds. So we have additional penalties on that. And then you have a cost of the set points that you're going to provide to these different devices. And this is where the controller is going to optimize the use of all of these different resources within the system in order to keep all of the variables within the desired bounds by making the minimal changes you need to the set points. And again, we have our model of the system, which is supposed to capture the relationship between inputs and outputs and the limits on the reference signals. And this is the kind of response you get. So this dotted line would be the response without our control scheme to a disturbance which occurs in the system. And the solid line here is the response with the control scheme. So you can see that the voltage is made to hug that lower limit. So you maintain the voltage within the lower limit despite uncertainties in the model and despite disturbances which are affecting the system and which would otherwise lead to operation outside of the desired operating range. Okay, so that was the first framework that I wanted to discuss, and I'll briefly now go through a second framework for thinking about this same problem. And this second framework, we primarily developed it focusing on frequency control problems, and so I'll show you an example of frequency control in a minute. This second framework, instead of beginning from the point of view of convex optimization, one instead goes back to control theory and thinks about classical problems of tracking and regulation in control. So that's where we're going to start. And this is sort of a standard tracking block diagram that we would study in automatic control. So you have a system called the plant that you have some inputs to. It's affected by disturbances, and you can take measurements. And you would like, for instance, this measurement Y to follow a desired reference signal R. And there's a standard methodology for dealing with these kinds of problems. It's a two-part design. So you compute an error, which is just the difference between the reference and the measurement. And that error is fed to something called a servo. That servo produces a signal eta, which is sort of the important part of the control signal, I would say. And finally, there's another piece which is called the stabilizer to ensure that the closed loop system remains stable. And this two-part design is very systematic and standard, and you can show it's sort of a necessary and sufficient design to solve these kind of tracking and regulation problems. And a lot of the theory behind this was developed, in fact, at the University of Toronto by Davison Francis and Wanham in the 1970s. So in the kinds of problems that I've been describing, they seem to be a little different than this problem here. We have some notion of making optimal use of different resources, and we also have a notion of constraints. We want certain variables to always lie within constraints. So this second framework that I'll briefly tell you about is trying to start from this basic idea of a tracking control loop and integrate in these other criteria that we would like to have. So this is the big picture idea of what we're trying to do. So we again have a plant here. I'm writing things out more explicitly now. This is our LTI plant that we want to control. And we're going to take some measurements from the system. We're going to feed those measurements to something I'll call an optimal steady state control servo. So it's sort of like the servo from the previous slide, but it's a modified design now. Then there's going to be a stabilization block just as before, and then that's going to produce a control input that goes to our system. And what we've really been developing in the second framework is a methodology for designing this modified servo here. So building a new kind of servo that can take into account optimality considerations and take into account operational constraints. So I think in the interest of time, I'm going to skip over much of the technical details here, and I'm going to go to the kind of engineering example that you can work out using this kind of theory. So it turns out the theory we developed is quite flexible, and there's many different options for designing this kind of servo, which we call an optimality model. So, yeah, I'm skipping quite a bit of detail here. The slides are available on my website, but in the end, what you get is a quite systematic design procedure for integrating these optimality and constraint criteria into classical tracking designs. Okay, I'm also going to skip this, in fact. So here's an example of applying this methodology to a simple control problem. So I'll show you first this example, and then we'll go to the power systems example. So here we have a plant which has 4 inputs. So we have 4 different elements of this vector U. We have 6 measurements for Y, and the plant internally has 20 states. Turns out that doesn't matter very much. We're going to use this framework in order to solve a sort of unconventional tracking problem. So I'm going to look at the error between my desired value for the output and the output. I'll look at that error, and what I want to do is I want to minimize the worst case value of that error. That's captured by this thing called the infinity norm. So it's sort of the worst absolute error that could occur. And I want my control input to stay within some bounds. And just to show you the flexibility, I also am going to include another constraint here. I want the sum of all of my control inputs to stay within some bounds. So I have individual bounds on each control signal, and I have a cumulative bound on my overall control signal that I'm going to provide to the system. And here's the kind of result you can get here. So what I'm doing in this simulation is I'm applying a bunch of disturbances to the system here, W, and I'm seeing how the controller reacts. So here's the tracking error that I'm plotting. We would like that tracking error to remain as small as possible. That's what we're saying here. And here's the result. So first disturbance hits the system. The controller tries to keep the tracking error as small as possible in either direction. So you can see there's sort of a symmetry here around 0. A bigger disturbance hits the system, we're not able to maintain the same quality of tracking error as we did before, but we try to maintain the smallest we can, and you can see this is symmetrical. So it's maintaining the worst case tracking error either in the plus direction or the minus direction. And the reason we're not able to get the tracking error all the way to 0 is because we've hit these limits here on our control signals. So if I plot the control signals, the limits here are +1 and -1. And you can see that my control signals, they've been limited to these upper and lower limits. So the controller is working to do its best to try to minimize that error while keeping the control signal within the limits that we specified. Okay, here's the power system example. So coming back to this idea of frequency control, we have set points that we can provide into the power system. The power system is disturbed by load and uncontrolled generation changes, and we measure frequency deviations coming out of the system. And we would like to design a controller using this methodology that's going to make efficient use of those different controllable resources within the system, subject to limits, and we want the frequency to be driven to 0. And we want to do this subject to the dynamics that are imposed by the power system. And a simple model you could use for looking at these dynamics is this linearized model here. So this is a model of how the generators dynamically interact with one another, and a simple model of the control system for the generators. And when you apply this methodology that I've mentioned, this sort of optimal tracking methodology, it turns out there's a lot of flexibility, and it reveals all of the different control architectures that you could choose in order to try to address this problem. So let me show you some of those architectures. So here's one architecture that you can get out of this control scheme. So in this architecture, there's one central controller, and the frequency measurements are brought from different points in the system to that central controller. The controller then sends out set points to other devices within the system in order to try to bring the frequency back to nominal. So this is similar to something called automatic generation control and conventional power system control. So that's a centralized design. You can also get distributed designs out of this approach. So here's a distributed design, and what I mean by that is now each unit here that's participating has its own controller, and the measurements from the power system are fed to that local controller here and here and here, but not to a central location as shown up here. Instead, what happens is the controllers now communicate with one another, and what they're actually communicating in this situation is not the measurements, but an internal state of the controller. And you can sort of expand this to much more complicated situations involving power systems with multiple areas and so on. I won't talk about that today, but you can push this kind of picture here quite a bit farther, and you can come up with all sorts of hybrid architectures between centralized and decentralized. And that allows you to start thinking about, well, what's the essential information that needs to be transmitted around the system in order to achieve your specified control objective. Okay, wrapping up, some of the ongoing work that we're looking at in this sort of broad area of designing these controllers that do some optimal tracking and regulation. So you can start to play around, for instance, with the projected gradient method from the first part of the talk and introduce additional terms there that affect the transient response. So this connects to something in control called loop shaping, and we're starting to look into that. On the optimization side, you can start to push the design of this approximate sensitivity matrix pi using, again, these methods from robust control. So you can not only analyze these kind of systems if you fix pi, but you can actually design pi to have specified properties. And that allows you, for instance, to control where information needs to flow within the system. So it allows you to control the information structure of how the controller is going to operate, what information is it going to operate on. And various other technical extensions that are sort of interesting, including possibility of learning some of these controller gains online instead of designing the controller offline. Continuing some of the work that I briefly mentioned that's going on with EPRI. So we're looking at again, these sort of hybrid centralized, decentralized control mechanisms for power system control when you have lots and lots of controllable resources. And one thing we're going to be starting to push on is transmission distribution coordination, where again, architectures, this word keeps popping up. What information is going to have to be sent where, and thinking about those control architectures. And in fact, we're going to be doing hardware in the loop testing of the control schemes that are designed here. I'm going to skip that, and I'll just conclude. So I've tried to give you a flavor of some of the interesting stuff that we're doing at the intersection of control and power systems. And really what the intellectual project here is to try to bring some of the newer ideas that are emerging at the intersection of control and optimization theory, bring those to power system applications while keeping the perspective that controllers that you design for power systems need to integrate very seamlessly with the conventional controllers that already exist in the system. And so we have two frameworks that we're sort of pushing in different directions in order to achieve that. Many more opportunities, I think, to push in this direction of control optimization and power systems. So, you know, we have 70, 80 years of fantastic control engineering and control theory that we can really bring to these kind of new intersection areas and talk about things like loop shaping and anti-wind-up design and methods like that. Another direction I think is quite interesting is, again, thinking about architectures, hierarchical control, competitive multi-agent kind of control systems, and thinking about learning-based control systems, again, in this context up here. Okay, so to sort of wrap up and emphasize one more time, what we're trying to do is develop theory that's solid, it's backed by rigorous analysis, but it's also practical. And I think when you develop really a good theory does end up being quite practical. So that's what we're trying to do here. We're trying to target an intersection of these kind of different design constraints. And I think there's an incredible richness of scientific problems just at this intersection between control and energy. So let me acknowledge some of my collaborators on this work. So Liam Lawrence was a master's student at Waterloo, at ENOSA, and Kevin, a PhD student and a postdoc who are at Waterloo right now, and collaborators at the Electric Power Research Institute in the United States, and at NREL and Johns Hopkins in the United States as well. So that concludes my presentation. Thank you very much for listening, and I'd be happy to take some questions.
Thank you, John. Thank you so much for your wonderful presentation. And now the floor is open for Q&As. And I see participants. So I would request participants to please go ahead if you have questions for Professor Simpson-Porco. Please go ahead. Well, I guess I can give you guys a bit more time to think about a couple of questions. But John, I actually received a question on my WhatsApp from one of our grad students, and I am gonna ask this question to you. The question says, which electricity generation technology is more challenging to deal with in terms of frequency control, grid stability, and power quality? And in brackets, the grad student said dispatchable versus non-dispatchable. But when it comes to dispatchable, that is coal, natural gas, nuclear, geothermal, which one creates more challenges when it comes to frequency control, grid stability, and power quality?
Well, in terms of the conventional controllable resources, typically it would be natural gas that's the easiest to work with because you can sort of ramp up and ramp down quite quickly. Um, uh, Nuclear, for instance, basically provides no frequency control at all. It just holds at a constant power level. So it sort of varies from resource to resource what's typically used, but excuse me. But typically in the conventional resources, natural gas is the easiest to work with. In terms of the sort of newer resources, it depends very much on whether you're talking about dispatchable or non-dispatchable. Of course, if it's non-dispatchable, by definition, you cannot do anything. If it is dispatchable, then typically there's a market mechanism that's working behind the scenes there in order to compensate those resources for participating in frequency control services. And so it depends on the nature of that contract. Typically, there'd be some limits that those devices would provide regulation between. And between those limits, they're contracted to provide whatever power that you want to request from them. And some of them can be quite fast. So flywheels and batteries can respond very quickly. So you can provide very high bandwidth frequency regulation with those resources, much faster, in fact, than even natural gas. And within Ontario, there are some attempts to try to integrate these faster non-conventional resources like batteries and flywheels into frequency regulation services right now.
Okay, perfect, perfect. And John, just for my own curiosity and from my research point of view, when it comes to deep geothermal electricity power plants that are very much available in Western United States, especially California, but unfortunately no such thing in Canada. Do you think doing like frequency control would be a problem when it comes to geothermal power plants?
Unfortunately, I don't think I know enough about the technology to really give a sensible answer.
Okay, no problem. We can actually discuss on this offline, I guess.
Sure.
Yep, perfect. So I guess I have given enough time to our participants. And if someone has a question, please go ahead. And if you guys don't have a question at the moment and you would like to touch base with Professor Simpson-Porco in the future, his email address is available in the public domain. You can always get in touch with him. And I will also be posting this video recording on the WISE YouTube channel and on the WISE website as well for anybody to view it in the public domain. And if you would like to share it with your colleagues, you guys are always welcome. So I'm going to ask again if there is any other question you guys would like to ask. Please go ahead. I guess not. So I would like to thank Professor Simpson-Porco for his wonderful presentation and sharing some great insights with us. John, thank you so much for your time.
Great. Thank you, Armagan.
Thank you so much. Have a great day.
Bye.
Thank you. Bye-bye.